Point Pleasant, West Virginia, December 15, 1967. At exactly 4:58 in the afternoon, 46 people died. The Silver Bridge had stood for 4 decades. Christmas was 10 days away, and the span was crawling with rush-hour commuters heading home from work, with children sitting beside wrapped packages in the back seats. A man unloading a truck on the nearby bank heard a sound like a shotgun. When he looked up, the bridge was already folding. It started on the Ohio side, and in less than 60 seconds, the entire structure dropped into the 44-degree waters of the Ohio River. 32 vehicles fell. Most who survived the initial impact did not survive the freezing current. The span had been routinely inspected. It was maintained to the strict standards of the era, and on that Friday, it was carrying a normal volume of traffic. Survivors pulled from the water all reported the exact same physical experience. There was no shudder in the deck. There was no settling or groaning metal. The roadways simply tilted and then fell. A massive, fully approved steel structure carrying millions of pounds of live load simply vanished from the sky with zero warning. Within hours, United States Navy divers were in the water. The current was strong, and the twisted steel was tangled deep in the riverbed mud, making recovery incredibly dangerous. Investigators from the newly formed National Transportation Safety Board arrived to map the wreckage. Their primary objective was to drag the suspension chains out of the river, piece by piece, and lay them out for forensic study. To solve the mystery buried in the mud, investigators had to look backward 40 years to the mathematical philosophy of the bridge's original design. When engineer J.E. Greiner submitted his plans in 1927, he chose what is called an eyebar-chain suspension. It was cheaper to fabricate and faster to assemble on site. Older spans, like the historic Wheeling Suspension Bridge, used similar eyebar chains and had securely carried live traffic for generations. A traditional suspension cable, like the ones used on the Brooklyn Bridge, is built from thousands of individual steel wires bundled tightly together. If one wire snaps in a woven bundle, the remaining thousands share the load. The structure holds, and a maintenance worker can easily spot the broken strand during routines. This diagram shows the completely different approach used on the Silver Bridge. The roadway hung from a chain of solid steel bars, each 2 inches thick and 12 inches wide. At every joint, 2 flat bars sat side by side, connected by a steel pin. There is zero redundancy in this arrangement. If one bar fails, the entire load transfers instantly to its partner, and that remaining bar was never designed to hold the full weight alone. The design of the chain geometry meant that the total structural integrity of the span rested completely on each individual steel bar. The origin of the collapse was traced to the north suspension chain on the Ohio side, hidden inside the eye of a single steel link known as eyebar 330. Over 40 years, moisture collected inside the tight space between the steel bar and connecting pin. Mixed with air pollutants from local chemical plants and coal-fired power stations, that trapped water became a mildly corrosive electrolyte. This specific environment triggered stress corrosion cracking. The constant, immense tension of the bridge's weight, combined with the harsh chemistry of the trapped water, slowly tearing the solid metal apart along its atomic grain boundaries. At the rhythmic vibration of thousands of vehicles crossing every single day, and the metal suffered corrosion fatigue. Each loading cycle pried the tiny pit open just a fraction further until the crack reached a depth of 2.5 millimeters, roughly the size of a fingernail clipping. On December 15th, the temperature above the river dropped to just over freezing. That specific cold crossed the transition temperature for the carbon steel used in the eyebars, making the metal highly brittle. The remaining intact steel ran out of margin. The lower limb of eyebar 330 fractured cleanly in microseconds, severing the bridge's only lifeline. The final report, issued 3 years later, confirmed that the microscopic cleavage fracture in eyebar 330 was the sole physical cause of the collapse. Investigators searched for negligence, but they did not find it. The original builders of the bridge did not cut corners. The inspectors who walked the span in the 1960s were highly trained, looking exactly where they had been taught to look. The failure was invisible to the technology of the time. When the bridge was designed in 1927, The concepts of stress corrosion and corrosion fatigue in rural structural steel simply did not exist in the engineering vocabulary. The collapse revealed a gap in 1920s engineering knowledge, proving that steel could succumb to chemical processes that designers didn't yet know to fear. The response from the United States Congress was swift. The Highway Acts of 1968 and 1970 created the National Bridge Inspection Standards, establishing the first strict federal rules for how often a bridge had to be checked, and by whom. Because visual inspections were no longer enough, this diagram illustrates how engineers developed new non-destructive testing methods. Acoustic ultrasound and magnetic particle inspections were deployed specifically to see through solid steel and locate subsurface flaws before they became fatal. Structurally, redundancy became an uncompromising, legally mandated design principle. No critical load path would ever be built without a backup. Today, every time an engineer scans a steel joint, or a designer factors an extra load-bearing cable into a suspension span, they are paying a direct mathematical debt to the 46 people who never made it home for Christmas.